You already know what a right angle is, but that idea generalizes far beyond 2D geometry, and when it does, it produces a special class of matrices that are trivial to invert and preserve both lengths and angles. In this video, we'll build up exactly what that means, starting from something you already know. Hey, welcome back. I'm Oliver, a computer science student and tutor. Orthogonal matrices is one of those topics where the name doesn't give you much. So today, we're going to build up from something you already know, perpendicular lines. By the end, you'll also see why orthogonal matrices are particularly well behaved and why that matters. So starting from the right angle as we know it, we might be familiar with another term, namely perpendicular. So for two lines to be at 90-degree angles to each other means that they are perpendicular. Orthogonality is just a generalization of perpendicularity. In truth, we can have orthogonality over more abstract things than lines or vectors, so they are relevant for all of linear algebra. But we'll just focus on the Euclidean vector spaces for today. Before we get to the formal definition of orthogonality, we first look at scalar products. The scalar product, or the dot product, is a type of inner product for the Euclidean vector space. Given two vectors a and b from our Euclidean vector space of size n, so n-dimensional, the scalar product between a and b, given by these angled brackets, is simply the sum of all products of the entries. So this would be the first entry of a times the first entry of b, plus the second entry of a plus the second entry of b, and so on. A simplified way of writing this is to transpose A and then do a matrix multiplication between this transposed of A and B. And this is equivalent to this form. We use this scalar product to compute lengths. The L2 norm is a norm which we are all familiar with. It is used, for example, in Pythagoras' formula and is defined as the square root of the scalar product of a vector with itself. And this tells us how long a vector is. For example, if we look at the vector 2, 2, and we plug it into our formula for the L2 norm, with our scalar product replaced with this matrix product, which we saw is equivalent, we see that the result is a scalar number, so a single number, and it is root 8. It tells us that this length here is root 8, and this is approximately 2.8. This is equivalent to using Pythagoras' theorem and seeing this triangle here with lengths 2 and 2 and saying that this side here, the length of it, is the square root of 2 squared plus 2 squared. That is the same as 4 plus 4 and taking the square root of that. Now this example was just for two-dimensional space, but this process for calculating this distance generalizes for all dimensions. So a vector space of dimension 10, of 100, of a million, for all of them you can calculate this L2 norm that tells us what the length is of a vector. Now there is a further definition for our scalar product, a geometric definition, which also gives us some better insight into what it means for vectors to be orthogonal. Here we can see that the scalar product of A and B is equivalent to the length of A, so the L2 norm, which we just looked at, multiplied with the L2 norm of B, multiplied with the cosine of the angle. So theta here is the angle between our vectors A and B. And this is precisely what gives us orthogonality. So while the length of each of the corresponding vectors has an influence on the scalar product, so does this angle. And this angle now directly correlates with our concept of orthogonality. So if this would be 90 degrees, this cosine would be evaluated to 0. So this whole part would become 0 if our vectors A and B are orthogonal. For example, seeing these two vectors A and B, which obviously have a 90-degree angle between them, this means that our theta is 90 degrees The scalar product is the product of both the lengths times cosine of theta, but because theta is 90 degrees, this cosine evaluates to 0, and the lengths actually don't matter. So this vector b could be this one, or it could be this one up here. And the same is true for a. It could also go into the opposite direction. We would still have 90 degrees in each case. And thus, the whole scalar product is 0. And this is always the case when we have right angles. So the result is, this is equal to 0. So the scalar product is equal to 0 when we have right angles. And this is exactly what it means for two vectors to be orthogonal. So we've seen that if a and b, if their scalar product is equal to 0, that means a and b are orthogonal to each other. Now this concept can be generalized to sets. So we have a collection of vectors v1 to vn, and we say that this set of vectors is orthogonal if each of their vectors is orthogonal to each other. Each of them meaning that unless they are the same vector, they are orthogonal to each other. So for all vi and vj, their scalar product is equal to 0 if I and j are not equal to each other. And then v is an orthogonal set of vectors. So now we know what orthogonal vectors are. What happens when we build an entire matrix out of them? For this, we need to understand what orthonormal means. Orthonormal is a combination of the word orthogonal and normal. We saw what it meant to be orthogonal, so for two vectors to be orthogonal, and now normal remains to be defined. We call a vector A normal if its length is equal to 1. And we saw that we use the L2 norm for this, which was the square root of its scalar product with itself. And when this L2 norm is equal to 1, then we call our vector normal. Now that we know what it means for a vector to be normal, we can combine it with orthogonal and we get orthonormal. So what we get is that an orthonormal set of vectors is orthogonal. So each two vectors that are different from each other have a scalar product equal to 0, and each vector itself is normal. So it has a length of 1. Now we get into the naming, which might be a bit confusing, namely that of orthogonal matrices. Orthogonal matrices are those that are real square matrices where its columns are composed of vectors v1 until vn that all have the size 1, so they're normal, and they are pairwise orthogonal, so their scalar product is equal to 0. Now the confusing thing here is the naming of orthogonal, since we just learned that additionally having lengths of 1 in each case makes it orthonormal. So perhaps a more fitting word would be that this is an orthonormal matrix. But nonetheless, the name orthogonal is still the used term for this. But so let's summarize once more. An orthogonal matrix is a real square matrix whose columns are orthonormal vectors. They each have a length of 1 and are pairwise orthogonal. Let us take a look at what happens if we transpose this matrix and multiply it to the left side of the matrix itself. So first, if we transpose the matrix, all the columns become its rows, and its rows become its columns. So we get exactly this form. Multiplying it with the matrix itself, we get in the first row, first column, the product between the first row of the first matrix and the first column of the second matrix. So we get the product v1 transposed times v1. Now when we multiply this first row with the second column, which would be v2, we get v1 transposed times v2. But now we don't have to calculate what this is because we know that these two vectors v1 and v2 are orthogonal. So the result will be 0. And this will be the case for all other values here because v1 is orthogonal to all other vectors except for v1 itself. Now we know that down here we will also get only zeros because each one of these values is the result of multiplying v1 with these lower rows of our first matrix. So from v2 to vn. And we know that for the same reason that these are zeros, these will be zeros as well. In this entry, we now get v2 times v2, so we get v2 and v2. And we get a 0 here and here again, and this process repeats because these are orthogonal. And this goes down until we get v transposed n times vn. And everything else is just zeros. So what we have here is a matrix which on its diagonal has values and all others are 0. What is interesting now is that these are not any values, but these are all 1. And why is that? Well, we know that v1, as well as any other vector, has the length 1. So this value here is equal to 1. What we have in our diagonal is always the scalar product. So it means that the scalar product, taking the square root of that, is equal to 1. If we rearrange this, we get that the scalar product of A with itself is equal to 1 squared. But this is just 1 again. So this scalar product, which in our matrix we have written as A transposed A, is equal to 1. And this is then exactly what we get in our matrix. We get 1s on the diagonal and zeros everywhere else. And this is exactly the special property of our matrix V, because this is just the identity matrix. So V transposed times V is equal to the identity. And if you remember from my video on matrix inversion, what this means is that the inverse of our matrix V is simply the transposed of that matrix. And this is an incredibly powerful property of our matrix V, because a process of inverting our matrix, which would usually be very costly, has now been reduced to simply turning its columns into its rows. And that is such a trivial computation that this is the fastest way to invert a matrix if it is possible. So for an orthogonal matrix, matrix inversion is completely trivial. Now, from the orthogonality of our matrix, in this case we're calling our matrix Q, we get 2 further properties: the preservation of length and the preservation of angles. The preservation of length for a vector v is that because we can write this scalar product, so this is the scalar product of q times v with itself, we can write this transposition in this way, because in the middle here we have our orthogonal matrix times its inverse, namely its transposed. We get that this is simply the identity matrix, and thus the result is we just get v transposed times v. If we now write the square root above each of these sides, this would be equivalent to the L2 norm. So we get exactly this, that q times v, the L2 norm of that, is equal to the L2 norm of v itself. So the length of the vector we get after transforming v using our q is just the length of v. So the length is preserved. The preservation of the angle is deduced almost equivalently. What we get is, this time we have 2 different values v and u. The scalar product of these is just equal to the scalar product of these vectors themselves. So applying the scalar product on the transformed vectors is the same as just using the vectors themselves. What's important now is that, as we've seen above, the length of these vectors is still preserved. So if we go to the geometric definition once more, we see that for the scalar product of v and u, we get this formula, and scalar product of v and u after having been transformed by q is this formula. What we've just seen above here is that these scalar products are the same. That means these two are the same. We've seen also that the length is preserved, so these are the same. And the only thing that could now differ is this cosine. So what we now have is that these two values are the same. And from this, we get that the angles are actually the same. There is the case where these two take the same value with different values here. So say we have 90 degrees here and 270 degrees here. Then both of them are 0. We actually consider these cases the same. So 270 degrees is actually just 90 degrees in the other direction. So the relation between the two vectors is still the same. We still have the same angle between v and u after having applied our transformation q. So given these two properties, that the length and the angle are preserved, this means that orthogonal matrices are essentially rotations and reflections. And that is why these sorts of matrices preserve structure in our vector space. This matrix here, which is just the identity matrix itself, is an orthogonal matrix. Now you can multiply it with its transposed, but another way to tell whether it's orthogonal is to check whether the two properties hold. All of its columns have to have length 1. So in this case, if we square each of its entries, 1 squared plus 0 squared, we get 1, so its length is 1. And in the second entry, 0 squared plus 1 squared is also 1. So they both have length 1. The only thing to check now is whether they have orthogonal vectors. And we see this if we multiply the entries piecewise and add them up. So 1 times 0 is equal to 0, and 0 times 1 is equal to 0. Adding these up, we get 0, so they are orthogonal. That means our matrix is orthogonal as well. If you want to go deeper, orthogonality shows up in a really elegant way in the eigendecomposition. I have a video on that here, and one on eigenvalues if you need the foundation first. Subscribe if you want more linear algebra, and as always, thanks for watching.